And in science, there is not a debate about the age of the Earth in mainstream geochronology, and geoscientists are highly confident that the Earth is about 4.5 billion years old. So let's look at some of those the evidence for that. So here is the geologic column again. This is the mainstream version where the Cambrian started 540 million years ago, and then the Triassic came along after a big extinction. The Permian ended with a huge extinction. That was about 220 million years ago. Then the Cretaceous ended with a big meteor strike and a large extinction event 65 million years ago. And that sort of wiped out the dinosaurs, but not all of them. Birds were dinosaurs, and we still have birds. So, but how do we know these ages are correct? There are lots of reasons. These can be compared to Humphrey's things like dating the radiocarbon and the mud and the salt and starlight and time. But these are actual things that are not radioactive that indicate the Earth is really pretty old. And there's a blog you can link to. But tree rings. Some trees have been dated back to, say, 5,000 years, but there are older trees that died, but we can form a continuous sequence of tree rings that gets us back to 18,000 years, which is 3 times the creationist age of the Earth. Varves are annual layers and lakes, and some of these lakes, fossil lakes, have thousands and thousands of layers, tens of thousands. So those prove that the Earth is older than 6,000 years. Stalagmites is one of the best evidences. I'll talk about these a little more. So to date, stalagmites, they use something called uranium series dating. Mostly uranium, and when you're looking at uranium changing to lead, that lets you look at very old events, billions of years. But it turns out that as uranium decays, and it's not necessarily uranium-235, but uranium-238, it decays into thorium. And then after just a few days, that decays into protactinium. And you get a what's called a uranium series. So if you measure these isotopes, you can kind of figure out where in that series you are. And so this allows us to use radioactive dating for samples that are, say, 10 to 50,000 years old. And it's all due to thorium. Basically, thorium is not soluble in natural water. So if there's a sample with a lot of thorium, we know it's probably pretty old. A sample with not so much thorium is much younger. So it's basically an equilibrium as this cascade occurs. So a technique, Victor Polyak, one of my classmates, studied this. This is from the Fort Stanton cave right here in New Mexico. And this is a thin section of a stalagmite. And they did uranium series dating for all these layers. So you can see, dozens and dozens of layers. And as you go deeper into the stalagmite, it gets older, of course. So these youngest layers, about 10,000 years old. The oldest layers, 50,000 years old, 60,000 years old, which is 10 times the age of the creationist 6,000-year-old Earth. So stalagmites prove that the Earth is 10 times older than the creationist estimate. And this uranium series dating is so precise that you can actually, do the uranium dating here, 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 and here, and then actually count the number of annual layers between these, and the number of years between these dates agrees with the difference between the dates. So just counting the layers agrees with the dates that we get from uranium series dating, which is phenomenal. I mean, that's incredible. So that's really accurate, and we can be highly confident that the Fort Stanton stalagmites are 60,000 years old, and we can count 60,000 years of deposition. Here is the Grand Canyon, a big problem for Noah's flood because this did not happen in a year. Here's a nice sort of picture. You've got tilted sediments, and then you've got angular unconformities, flatline sediments. So this shows that these things weren't just all jumbled in one big flood, but first you had deposition of sediments, then they became lithified, then they were folded by tectonics and uplifted, and erosion planed them off, and you had subsidence, deposition of more sediments, lithification of more sediments, more uplift. So it's a complicated history. This is why geologists get their paychecks. And here's a great example. Here's North America over here, and you can see Spain and Great Britain over there. And this is a magnetic image of the seafloor between North America and Europe. And you can see these layers that form parallel layers. And what we think happens is that the mid-Atlantic ridge, mid-oceanic ridge, that's where new lava bubbles up and it pushes these magnetic layers on the western side. They're pushed toward North America. On the eastern side, they're pushed toward Europe. So this layer here is about the same age as that layer there, and we've dated them and proved this. So what we can do is measure the current rate of expansion. We can just put GPS units in Manhattan and in Lisbon, Portugal, and see how fast they're moving apart, and it's just like a centimeter, maybe 2 centimeters a year. We can measure this distance from New York to Portugal and calculate, hey, this for this much separation to happen, it would be about 200 million years old. So we think the Atlantic Ocean is about 200 million years old. One of my favorite evidence for the age of the Earth is the absence of short-lived radioactive elements. So in the periodic table, there was a blank spot, number 43. It was empty for a long time until we finally whipped some up in a radio lab, and it turns out to be radioactive. So in 1937, we produced some technetium artificially, and its very name, technetium, is Greek for artificial. But we found, once we had some, that its half-life is 2.6 million years. So if Earth was created 6,000 years ago, and there was technetium when it was created, there would still be 99% of that original technetium. So God, must have really not liked technetium when he created the Earth 6,000 years ago, or maybe the Earth is old. Technetium is man-made. We can see it now that we know what it is. We've measured its spectrum, and we see its spectrum inside many stars. It's a part of solar systems all over. So in fact, every single radioactive element that has a half-life less than 80 million years are curiously absent from the Earth. Lead-205 has a half-life of 15 million years. There's none. We have to create it in a lab, just like technetium. Hafnium-182, 9 million years. Lots more. So if the Earth was created 6,000 years ago, the Creator must have had a very strange antipathy for the very elements that would have supported the young Earth hypothesis. But using Occam's razor, that's a pretty tentative explanation. The simpler explanation is the Earth is really old. It's billions of years old, and we don't have these radioactive isotopes because if Earth had them when it was formed 4.5 billion years ago, they would have decayed by now, and we wouldn't have any, just like we don't. So the simple explanation is that the Earth really is old. So I've got a little film clip, and whoops, who asked for that? So this is a video I was going to show earlier, but we just ran out of time. There it is. Now I'm going to speed ahead to the beginning. This kind of pedantic, so we're just going to get to the good part here. Right about there.
Here's where it gets tricky. It's true, you can measure a decay rate using observational science, but there's another kind of science that is required to accurately calculate dates for rocks, and that is what we call historical science. Historical science deals with the things in the past, and therefore it cannot be repeated and tested. Dating methods require both types of science, because in order to get accurate rock dates, one would have to accurately know both the decay rate and the initial conditions of the rock sample, right? Since radioisotope dating uses both types of science, we can't directly measure the ages of rocks. There are assumptions involved. For instance, how do we know what the initial conditions were in the rock sample? How do we know the amounts of parent or daughter elements now in that sample haven't been altered by other processes in the past? How does someone know the decay rate has remained constant since the rock formed? The answer is they don't. Let's simplify again and talk about a typical hourglass. Let's say you walk into a room and you see an hourglass with sand at the top and sand at the bottom, and some sand sprinkling from the top chamber to the bottom. Well, observational science would allow us to see and measure the sand, and then calculate how long the hourglass has been running, right? We could make our sand measurements and then calculate when the hourglass was turned over, right? Well, those calculations could be wrong, because we may have failed to consider some major assumptions, like, was there any sand at the bottom when the hourglass was turned over? Has any sand been added or taken out of the hourglass? Has the sand always been falling at a constant rate? Since we did not observe the initial conditions when the hourglass started, we haven't been watching the sand all the time since then, we must make assumptions. All three of those assumptions can affect our time calculations. Now, of course, there's more to understanding all of this, but
so that's a really slick video, well produced, and doesn't mention Adam and Eve or Noah's flood. But boy, is it full of pseudoscience. So basically, they say there's historical science, and then there's actual science you do in the lab. And to date rocks, you have to use both of those. So you're making assumptions. And they had three assumptions they looked at. So this shows the hourglass analogy, a great analogy. You have a parent isotope that decays to a daughter isotope. And nuclear decay occurs at energies much higher than mere chemical reactions, and they are not affected by huge pressure, chemical, or temperature variations. You can have these things be hot, bathed in acid, put under huge pressure, and these radioactive clocks take a licking, and they keep on ticking. So here is the radioactive decay differential equation. N is the number of radioactive atoms, and K is the decay constant. And so the rate of change, how many radioactive decays you get per second, is minus this constant times the number of radioactive atoms. So here we have a small piece of uranium and a Geiger counter, and we're getting a very low count, just like a click, 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 click. But we can make this go up. So one way to make it go up is if you make the K higher. If you use, say, an element like germanium, which decays much faster than uranium, and it can decay so fast that a small chunk of germanium will make that Geiger counter meter go way up. It'll be going click, 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 click. It'll raise the hairs on your neck. You'll be wishing you had a hazmat suit. DNDT got big. And the other way to make DNDT big is if you have your old slow uranium, but you have a lot of it. If you have a big N, then that Geiger counter is going to go clickety clickety click click click, and the needle's going to swing toward the right. So that's the differential equation. Its solution is, of course, this exponential, the well-known exponential decay, where in one half-life you get to 50% of your isotope, another half-life gets you to 25%, 3 half-lives, 12.5%, 4 half-lives get you to 6.25%. So the ratio of daughter to parent is related to how old the sample is. So a young sample, you won't have much daughter, but an old sample, you'll have a lot more daughter product, and that's going to be old. So that's under ideal conditions. But what if some daughter element was present at time 0? Or what if daughter elements were pulled out of the hourglass, so to speak, by a magical process or a geochemical process, perhaps? So here are the top 3 creationist critiques from that Answers in Genesis video that we just saw. The first one: how do we know what the initial conditions were in the rock sample? And the hourglass analogy, we're making the assumption that there was no sand in the hourglass at the bottom. But if there was sand, then that would be historical science that throws the whole thing out of whack, and we don't know how old that rock is, do we? So science has an answer for this. It's called nuclear isochrons. Basically, nuclear isochrons is an advanced geochronology method that allows you to measure, was there any sand in the bottom of the hourglass when this thing started? So here's how it works. Here's an actual nuclear isochron of a sample that was measured at 4.6 billion years old, plus or minus 0.07, and this is the amount of daughter product, an actual fraction. So it requires 3 isotopes. So for rubidium, 87 rubidium decays into 87 strontium. So basically, one of the protons turns into a neutron. It's got the same mass, 87 protons plus neutrons. And then there is a third isotope, also strontium, but it's the normal non-radiogenic strontium, 86 strontium. So when the rock was formed, it can have both the daughter product, 87 strontium, and the regular run-of-the-mill strontium, 86 strontium. So what you do is you make a normalized graph where on the horizontal axis you plot the ratio of and you measure these minerals. You measure the 87 rubidium and normalize that to the 86, the non-radiogenic strontium. For the vertical axis, you measure the radioactive strontium and divide the daughter product and normalize that by the non-radiogenic strontium. So they're both normalized by the same things, which is what makes this graph turn out correct. So if you have a sample with a lot of rubidium, then in 1 half-life, this shows 1 half-life, we're gonna lose half of that original amount of rubidium, and it's going to change into an equal amount of strontium 87. So basically, if we look at the time evolution, it's going to go from here to here. If we have a mineral, just maybe a grain from a sample that doesn't have as much rubidium, then there's not as much rubidium to decay. When half of that decays, this path from here to here is going to be smaller. But the key thing that makes isochrons work, and the very name isochron, same time, which means that if these things started off flat at time 0, they will make a straight line as time evolves. So minerals with more rubidium are going to have a bigger jump, less rubidium, a smaller jump. And the slope of the isochron at one half-life will be 45 degrees. So here is a hypothetical diagram that shows different isotopes of strontium 86 and 87, and they're getting melted. They're getting mixed together to where they form a uniform thing right there. And that's how this method works. Just like if you take ink, dissolve it in some water, if you don't, stir it, it's going to be clumpy. But if you stir it, it'll be a uniform gray. That's what this melting is. So this is a key part of isochrons, is that your sample, when it was formed, it had to be molten hot, so that both of these isotopes, the normal 86 and the radioactive 87, which was there at the beginning, they would be put at the same ratio. So that's what melting does for you. And then here is the 3 billion year evolution. So I've got the radioactive in red decaying to the daughter product in green. There's one half-life when they were equal. And you can see, we'll let it go through one more time, but as time evolves, this isochron becomes steeper and steeper. So it's gonna, when it gets to 3 billion, it'll just start over. There we go. Starting over mostly rubidium. You can see the big jumps. The minerals with more uranium have rubidium have bigger jumps than the ones that don't. And then the jumps get smaller as the amounts of rubidium become smaller because it's decaying. But the cool thing is that this straight line, the slope tells you how old it is, and where it hits this x-axis tells you how much daughter product. See where that is right there? That's going to be the same point no matter how old the sample is. It's going to point to, was there sand in the hourglass when it was turned over? Was there how much of the radioactive daughter product was present with the non-radioactive at time 0? So that's what makes this thing work. For one half-life, you get this beautiful 45-degree curve. That's when the radioactive parent and the daughter have equal amounts. And for one half-life, you get 45 degrees. 2 half-lives, the slope plus 1 is 2 to the number of half-lives. So 2 half-lives, that's squared. So that would be 3. The slope of 3 would be 2 half-lives. A slope of 7 would be 3 half-lives, and so on. So, but this technique depends that at time 0, they were all mixed up and flat as could be. So at time 0, you also point to the same, about a 0.6 ratio of non-radiogenic to radiogenic to non-radiogenic strontium. So here is a sample that was invalid. So this sample was not melted at time 0. Maybe you just had a conglomerate where you took different pebbles and you mashed them together to make a conglomerate. And because they were not uniformly mixed at time 0, and this is over 3 billion years. So this is not what geologists see. When geologists do an isochron, they just get one of these for whatever 2.5 billion years or 2 billion years. But we can see if it starts off not straight, not a good sample, it never straightens out. That it's always got enough big kinks in it. So this is part of the quality control. And here's another. It starts off flat, starts off great, but at 1 billion years, we're going to pull some daughter product out through some chemical process. And once that happens, even if it only happens once, the straight line is spoiled for the rest of time. No matter, even if it's 2 billion years later, it's not going to be a straight line. So we have a little quality control. If you have a nice straight line there, then you have a valid isochron. The slope tells you the age, and the intercept tells you the initial ratio of dot product, how much sand was in the hourglass at time zero. If you have like a conglomerate that had a big, that wasn't uniform at time zero, it's never going to straighten out. And so when you measure it 2 billion years later, you can tell this is not a good isochron candidate because it's not a straight line. So this one's invalid because the sample was not melted. And if you have a sample that was melted but then had some isotope removed at maybe 1 billion years into its existence, it's never going to straighten out. So that one's invalid because daughter was removed at some point during the last 3 billion years. So isochrons provide a robust estimate of the sample as a fit of many data points. They provide a precise measure of the amount of initial daughter product, pretty cool. And they include quality control that shows if a sample should not be used because maybe it was a conglomerate or maybe there was some loss of daughter product. So if you were to look at your watch and it said 10 after 10, and the grandfather clock said 10 after 10, and clock across the street said 10 after 10, and as you walk into your office, 10 after 10, and the digital clock 10 after 10, you'd start to think, maybe it's 10 after 10. If different clocks give you the same time, that gives you some confidence that's really what time it is. And it's the same with radioactive dating. So there are several isochron methods. Rubidium, strontium, we just talked about. These have been used to date meteorites. The Earth, because of plate tectonics, things are churned up so much that we really don't have any rocks on the Earth that are 4.5 billion years old. So we assume that meteorites condensed at the same time as the Earth did when our solar system formed, and meteorites land on the Earth. We can measure them, and they turn out to be consistently about 4.5 billion years old. But it's from different clocks. So we've got the rubidium strontium clock with a half-life of about 49 billion years, and that gives an age of 4.5 billion years. We've got a couple, rubidium strontiums from different meteorites. Argon is about a 50th of that, 1.25 billion years, and the age still comes out 4.5 billion years old. And here's a samarium neodymium isochron that has a half-life of 106 billion years. So we've got these different clocks that tick at different rates. They're different by 2 orders of magnitude, from 1 billion year half-life to 100 billion year half-life, but they give you the same age. So it's like looking at all those clocks that had the same time. We have a high degree of confidence that those meteorites, and therefore the Earth, are 4.5 billion years old. So isochron is cool. It tells us when a sample is not good, but we can't get the age. If there's a kink in the isochron, we can't really tell how old it is. But what if there was another method that could tell if a system hasn't always been closed and could also provide the age even for systems with profound daughter losses where you take the daughter out during the lifetime of that rock? So in the creationist movie, they said, how do we know the amounts of parent or daughter elements haven't been altered by other processes in the past? And the hourglass analogy, has any sand been added or taken out of the hourglass? Those are great questions. And the answer is a method called Concordia Discordia. And it's a sort of tricky method. It requires 4 isotopes. We do it for uranium and lead. And there's two isotopes of uranium-235, the good stuff for A bombs and nuclear power, and it decays into lead-207 through a certain number of alpha decays, and that has a half-life of 700 million years. And then we have the slower uranium-238, much more common, and its daughter product lead-206, I think 8 alpha decays, a half-life of 4.5 billion years. And so we take some samples and we measure the 4 isotopes, the 2 of uranium and the 2 of lead. And you draw this perfect ideal curve, and the x-axis, the x-coordinate, is the ratio not of radioactive to daughter, but you put the daughter on top of daughter to radioactive. So for this uranium-235, we can see at 3 billion years, most of the uranium has decayed into lead, and so there's a lot more lead than there is uranium, and in fact that ratio at 3 billion years is going to be about 18. So that's the x-coordinate. We can see the x-coordinate goes from 0 to 100. So we have the fast uranium for the x-coordinate. For the y-coordinate, we use the slow uranium, 238, and at 3 billion years, you haven't even got to 1 half-life. You've got more uranium-238 than lead-206, and so the ratio of lead to uranium is less than 1. It's going to be about 0.6. So basically, you can make this theoretical curve that shows as you advance from 0 to however many billion years you want, you get this nice sort of curvy ideal curve. And because lead is very volatile, if you have a molten rock, all the lead is going to just evaporate out of that rock. It's volatile, it'll be outgassed, and so you'll have 0 lead to start with if it was properly melted. So here is the 5 billion year evolution. We can see the uranium-235 is going much faster than the uranium-238. 2 billion years, we're coming up on 3 billion years. We haven't even got to 1 half-life for the 238. Now we're just getting to 1 half-life there. Very much more than half-life there. So you get this ideal curve. So basically you measure these 4 elements and you see where they fall on this ideal curve. But let's suppose that at 3 billion years, things really got hot. And so you expelled some lead, and the 2 kinds of lead, 206, 207, chemically, they're the same thing. They're only 1 neutron apart. So if you lost 17% of the lead, your sample would move to here on the chart. 33%, it would move to here half. It would move to here, 67%, 83%. And if all the lead was gassed out, you'd be back at 0. So, but the cool thing about Concordia, Discordia is that once you get one of these events where you have lead being dispersed because it got real hot, the lead, some lead was expelled. Here it comes, boom, and once that event has passed, the lead with 0 will go up the traditional curve. The lead without any expulsion would stay on the curve at the high end, but you'd have all the points between, say 70, 80, 50, 30, 20%. That straight line remains a straight line. So this end of the straight line tells you how old it is. This end of the straight line tells you when this heating event expelled the lead. So here is an example from, this is 1 billion years after this. And we can see this point has moved to here, but it's still a straight line. That's the important thing. So here is the rock that went around the classroom, the Morton gneiss, and basically we don't have any samples at the extreme edge of the Earth. We just have a bunch in the middle. About between 40 and 60% of the lead was removed. But if you have enough samples, you can make the straight line. You can tell what that straight line is, and where it cuts on this end tells you this rock is 3.56 billion years old, and where it cuts on the left end tells you the heating event that expelled this lead from here down to here, about halfway. That was 1.85 billion years ago. So this method allows us to say, yeah, even though daughter product was pulled out, we can measure when that happened. 1.85 billion years ago is when that happened. So that is pretty cool. The third critique, sort of running out of time. How do we know radioactive decay has been constant? There are all sorts of methods for that. Talked about Oklo, basically we've looked at the fission tracks from Oklo 2 billion years ago, and they're the same as fission tracks now. So radioactivity has not changed in 2.5 billion years. So that's a good one. So that's the moral of Oklo. Also, we get confirmation of the uniformitarian hypothesis. This study looked at supernova 1987A and allows us to conclude that the speed of light has been constant for 168,000 years. Looking at methanol, we can see that the ratio of protons to electrons has been constant for billions of years. So basically, those three creationist critiques have all been answered. Conclusion, scientific data shows the Earth is 4.5 billion years old. Creationist attempts to prove it's young are flawed by errors, disregard of contrary evidence, oversimplified models. I call for having a little respect for our very old planet. So don't forget, we have a creation evolution essay or quiz or both due October 2nd. Starting Thursday, we'll have a quiz on this week's lectures. Really don't have time for the soapbox. So Thursday, we will look at genetic algorithms, which is basically evolution boiled down to a computer program. So if anybody needs the attendance, come on up and get your John Hancock down there. We'll see you Thursday. We'll look at genetic algorithms.